Yeah, yeah, fine.
We edit all this bit out anyway. But so when I start, so people are joining now. I can see they're 11:13, rapidly picking up. So that's good, excellent. I was just saying, Keith, when we started this process, I didn't expect that we'd have more people on our webinars than you get at an English Premier League football match. But it looks, unfortunately, that's what seems to be happening.
I know.
Obviously, we're biased here, but I'm quite looking forward to seeing a bit of soccer. They've been having some interesting debates as to whether they should have the sound of a crowd on the empty stadium or not.
I know. I was looking at all that, you know. Oh, by the way, going back, I've just been looking at that Annex 6. Okay. So, I've got a reasonable answer.
We won't start. Obviously, we've got 50 people online now. So, but the numbers are revolving upwards very rapidly. So, we'll obviously wait. It's not even 2 o'clock yet. So that's. So we'll wait and get started promptly.
Another minute or two, yeah.
But so we'll answer Engineer Mohammed Azjad's questions from Pakistan when I hand over to you after my introduction, Keith. And
yeah, you ask the question and then I answer it, eh? Yeah.
that would be a good thing.
Yes, you'd be there and ask it on his behalf, and then I answer and say, okay, before we go, we're going to answer these.
Okay. Right. So, yes, I don't want to leave it too long today, but it's not even, according to my computer, it's just this moment turned 2 o'clock. So we'll just give a few more moments to let people join up, and then we will get started. If I do my introduction, it doesn't matter if people miss that anyway, because it's you they want to hear, Keith. You're the star of the show. So, right, I'll just wait for it to click at 1 minute past, and then I will start. We'll get started promptly. So it's an overcast day here in Rugeley. No blue sky whatsoever, but not such a bad thing after the hot weather we've been having in the last few weeks. How about you, Keith?
Say again?
How's it down in your part of the world? Blue sky?
Cloudy and overcast.
Right. For those of you that don't know where we're TMS is situated roughly in the middle of the UK, just north of Birmingham, and Keith lives to the east of Birmingham, but the office is just to the north. But obviously, on a day like today, it doesn't really matter because we all live in Zoom world. Now it's just clicked 1 minute past 2. We have 70 people online, so let us get started with no further ado. I'd like to welcome you all to the 3rd TMS Tuesday. My name is Robert Shapton. I think most of you know me by now. I'm Managing Director of TMS Training Solutions, and I will be hosting today and introducing Keith, who you can see on your screen. The presentation today will be following on from last week, where we had a few technical problems, as I think most of you anybody that was on the online last week will be aware. Keith will be continuing on with discussion about the AGL circuit, power supply system that supports it, looking at remote control systems, and then talking about new technologies and collaborative decision making, CDM, that those of you that were on the mainstream webinar earlier may have heard some discussions from some of our industry partners about. And then we're getting on to that very important topic of electrical safety. Now, recognizing that there's a lot of important content and some of the technical hitches we've had in the past couple of weeks, we may, rather than rush things, we may go on into a 4th week. We'll decide that based on progress through the course of this seminar. And then, as promised last week, we will be planning follow-on seminars, which will be more in the nature of a presentation followed by a Q&A session, answering any questions you might have, covering the areas of PAPIs, PAPI sighting, the history of PAPIs, what they do, how they work, everything you could know. Tony Smith, the inventor of the PAPI, has very kindly offered to make a presentation to you on this topic, which will be the subject of further emails, further communications. We'll be talking more about safety and maintenance of visual aids. We will do that again with a presentation, but mainly Q&A session with a panel of experts to answer your questions. And then we will host a third webinar on the topic of asset management and how to manage your AGL in the world of the next generation of aviation professionals. So that's what's coming. Just to bring you up to date, I think most of you, you'd have to be living on a different planet to know that the unfortunate events of the last 2 or 3 months are continuing to have a severe impact on our industry. Some operations are starting. I read that Wizz Air are starting some very limited operations, but by and large, passenger traffic is not happening, certainly in large parts of the world. And it's further impacted for the UK because we have introduced, in our wisdom, new quarantine procedures, which are largely being reciprocated with our destination countries, which means that on departure and on arrival back in the UK, flyers will have to take 2 weeks in quarantine, which is basically stifling any potential for start-up of our aviation outside of cargo traffic. There have been some documents produced. ICAO produced a document of updated the documentation on COVID-19 and safety risk management. As I said last week, the key thing for us all is to be prepared, is to do a risk assessment, is to put in place risk mitigation processes and procedures in relation to our areas of responsibility, and above all, carry on our planned preventative maintenance. Because that way, if we can, we will be able to maintain safe operations as and when flights commence. Because safe operations apply to one flight as well as they apply to 100 flights. So be prepared is the key here. So without any further ado, I'd like to introduce you to our keynote speaker for today. Once again, Mr. Keith Costall, Principal Trainer and Director of TMS Training Solutions Limited. As you know, Keith has over 50 years experience, world-renowned expert in our field. And today we'll be talking about the circuits, electrical circuits we're working on, the power supply systems, electrical safety, and new technologies. So without any further ado, Keith, I'd like, if you'd like, I think you have a shared screen. If you'd like to put on your presentation and get started, we'd like to listen to you, please.
Well, good afternoon, everybody. Afternoon in the UK, good evening for some people, and good morning for others around the world. As Robert has said, you know, last week we had some technical problems. Unfortunately, I was outside my control. My area network went down. So thank you very much to the service provider for that, the network provider. They're offering nearly 4G and 5G. I would have liked 1G last week. So in line with that, I'm just going to run over a few things which we did cover early last week and then move onwards to the planned schedule for this webinar 3. Let's just go back this stage. Safety, compliance, and competence are the 3 key issues. Safety is probably the highest priority, both for the aircraft and for us, the personnel. But to be able to meet the safety, the compliance requirements, and be competent, you must have knowledge. It's okay gaining knowledge, but how do you apply that knowledge? You need to have the skill, and you apply it into the skills. And in line with all that, you've got to have the attitude. It's no good saying, oh, I've worked here for 20 years, you can't tell me. And I've heard that. Believe me, I've heard that. Yet, when I watch that very same person, they make multitude of mistakes because bad practices in the field without getting updated knowledge and applying the skills of today, then sometimes bad practices get passed on, and we don't want that. So what we probably have been able to impress in the past is when you're looking at knowledge and when you're looking at skills and applying that attitude, then we need to have a fundamental understanding of what your particular airport needs. And your particular airport is going to be unique. There is no two airports the same in terms of the facilities, the layouts, etc., the way it's managed, etc., etc. But overall, the compliance side is the same. If you've got a runway, your lights have got to be compliant. If you've got a taxiway, they've got to be compliant. And we must have maintenance associated with that. So when we do a training needs analysis, it is associated with looking at your facility. And as I explained last week, we use the ADDIE principle to analyze. We design your competency training, develop it with you and implement it, and then we assess. Because in today's day and age, it's not just having competency-based training, it's competency-based training and assessment and justifying that to the regulatory bodies. So I'm not going to excuse myself for showing this slide and the next one very early in this week's presentation, because we know that AGL is potentially a very dangerous electrical system. Why? We have voltages in excess of 1000 volts. And from an RMS voltage viewpoint, root mean square for those electricians or non-electricians, then up to 5000 volts, 4545 volts on a 30 kVA CCR supplied system. And in the event of open circuit, that is earths in the field, then, and which we have many, all of us, then we could have many times that before a CCR actually trips out. So I'm going to show this. The electrical hazards that are quite applicable to us is the shock, explosion and burns. And we don't want this to happen to you. So we say right at the beginning, do not disconnect a connector on a live airfield ground lighting circuit, because you could be injured seriously or killed. We don't want that to happen to you. If you're lucky and you're in that situation and you're not killed, perhaps this would happen to you. These are serious burns. Now, remember, in electrical engineering, voltage burns, current kills. And at 10 milliamps, a human being cannot let go of a live electrical circuit. We have 6.6 amps at maximum. So current kills, voltage burns. And in all our nations, wherever we are in the world, whether it's an authority or whether it's a national standard or it's just an airport engineering standard, then we must be qualified. And we must demonstrate that qualification and we must demonstrate that competency. So we must be authorized to work on AGL electrical circuits. But not just authorized to work on AGL electrical circuits in the field. So we have to have that understanding of airside operations. So we've already dealt with operating airside safely. Now we're going to be dealing with the AGL as a circuit and electrical safety. So there's some key issues that we all must adhere to, abide by. Unfortunately, many airports do not. Many airport authorities still think of the AGL person, he or she changes the bulbs in the field. Now we know it's different to that in today's day and age. So there's some key safe working procedures that must be adhered to. They must be available to us all. So where do we fit now into this wider operational area of airport and aviation operations? We are clearly today not just bulb changers. Our AGL system is part of an integrated system under collaborative decision making, and in more closely to us, we are part of a surface movement guidance system, which is part of the CNS of the operation of the airfield. The CNS, what does it stand for? Communication, navigation, and surveillance. Communication, we've got to communicate. It's clear, but we communicate not just verbally by asking permission to go around the airfield to the location where we're required. It's all about electronic communication in real time. And we are part of the navigation system. Ground traffic management. It is navigating the aircraft safely from the runway to the apron for parking and vice versa back to the runway for takeoff. And you can only do that safely if you know where the aircraft is. Therefore, surveillance comes in, and there are different forms of getting the location of the aircraft on the ground on a taxiway network. It could be induction loops, it could be a microwave sensor, radar, or ground movement radar, multilateralization. There's a multitude of systems that are available to us. And the regulatory bodies, interestingly, the regulatory bodies have said after this COVID-19, then technical staff have got to be competent to perform their job and in adequate numbers. So we need to have all our guys up and ready and be able to not just operate, but to maintain our AGL systems. So safety, compliance, and competence are just rolled all together. We cannot get away from it. So let us move on to what we've done in these webinars. In step one, the first week one, we dealt with safety, working safely airside, but it was in the form of 2 videos, which we didn't go through, that they're available, that were available to you online, and hopefully you've had a look at those. 2 good FAA, the US Federal Aviation Authority videos, excellent videos. So then last week we were dealing with step 2, Airfield Ground Lighting, and we had introduced ourselves to the standards, the layouts, the principles of AGL, etc., supported by a video that was available online to you. And we'd started going through the power supply and the AGL circuit before we were rudely interrupted in what I call BT OpenReach, the network provider. They decided not to tell everybody that they're going to work on the system, and then something happened, and probably one of their staff was not competent because it kicked everybody offline. So anyway, so this week I'm going to go back to the power supply, start with the power supply system again, go through the AGL circuit into remote control, and look at some of the operational needs and some of the alternative technologies that are available to us, supported by a video, and some of the advances and the alternative advances in technology that could be available from the various suppliers. So, because we're non-aligned, we're an independent group, so we're non-aligned to a particular supplier. So we are mentioning various AGL suppliers in our webinar. And then finally, we'll have a dedicated session on electrical safety, which is really close to my heart. And there is a video that's going to be available to you online to support that. So let's go into the power supply technology. Last week, and I remind you again, then we split AGL into 3 simple blocks: power, control, and the lighting. And that's how we're going to explain it. So when we're looking at power, where does the power come from? Well, it comes from a power station, from a local supplier. But we need to have standby power, and in the event of main power failure. So our substations or volts or whatever we call it is, our CCRs, our constant current regulators, that actually provide the power to the lights, then they have to receive an incoming electrical supply. Now, it is constant voltage. So in our substation or volt, we take the constant voltage and we convert it to constant current output. That's at the CCR. But in the event of that losing that constant voltage input, then we have to have some standby equipment, because we, depending on the operation of the airfield, the aerodrome, then there's category 1 operations for instrument runways, category 2, category 3 operations. And for category 1, in the event of power failure, we have to get our lights back on in 15 seconds. 15 seconds. For category 2 and 3 operations, we have 1 second. Now, the traditional way was to have a diesel genset. And when we went from category 1 to category 2, 3, we actually ran the AGL from the diesel genset. And we used the ring main as the normal supply as the backup, because we could change over within that time frame. But the modern way of doing it is to have a UPS. So from a standby power, we have the diesel genset and a UPS. Now we started off with rotary GPSs, and now we're into the world of static UPSs. So that is what we have today. But then within the substation, once we got that constant voltage electrical supply, and we got to feed it to the CCRs, then we have to do it through a distribution network. Now, that distribution network needs to have some safe working procedure capability. That means to be inclusive of some kind of lock-off device or isolation equipment. If you do not have that in your equipment, in your substation or vault, which if it's been there a lot of years, you may not have it, then you need to have some clear, safe working procedures and processes in place. The diesel genset, well, it's a diesel engine. It could be diesel engine. Well, that's mechanical engineering. Now, somebody's got to maintain that. Do you? Well, you're an electrical engineer. Oh, do you know anything about mechanical? So, there is multiple trades involved here associated with AGL. The UPS, whether it's dynamic, a rotary, or a static, then there's a lot of equipment in there, and it's controlled electronically. So do you have electronic engineering capability? A real valid factor. And when we come to the CCRs themselves, traditionally, in the IKO world, then we have been using the thyristor bridge principle in CCRs for a lot of years. If you go to the US, there are many CCRs that are ferroresonant CCRs. But in more recent times, the transistor-based CCRs, the IGBT, and now the high-frequency IGBT CCRs are in the marketplace. There is some very fundamental technology changes in that respect. And I've just brought up 2 circuit block diagrams, flow diagrams, which explain. And I've taken this diagram, and this is where I say we're non-aligned, but I've taken an ADB SafeGate thyristor-based MCR3 as a flow diagram, and I say it's a thyristor-based unit. And basically, we have thyristors And these thyristors are units which basically switch. So every half cycle, they go switch, 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 switch. And that's the basic principle of a thyristor. And then if we want to have current control, which we do, because in AGL, as you know, we don't just switch on the lights and leave them on. In daytime, we have them on high intensity, the highest intensity, and in the nighttime, we have them on a lower intensity or foggy, clear conditions, you know, vice versa. So there is a whole range of intensity levels. Internationally, for runway-related lights, there are 5 steps. Not all nations have 5 steps. Some have 6 steps, etc. But for taxiway networks, then generally speaking, we have 3 steps of intensity levels. So if you've got a thyristor base unit, then we switch on and off the thyristors according to the intensity. Yet when we move to this diagram, which is the low harmonic, which is the IGBT, then it's different. We sample out of a sine wave for our intensity levels. So basically, that's, you could very simply say, how does a thyristor work? Well, it's a switching mechanism, whereby an IGBT, a transistor-based, it's a sampling mechanism, you know, where it uses something called PWM in the technology, pulse width modulation. I'm not going to go into what pulse width modulation is because it's a whole subject on its own. And, you know, if you'd like to go to Wikipedia, there's a wonderful explanation how it works. But if you do wish to have some detailed training on the various technologies, then we can give it, right? They're dedicated courses. Moving onwards, not all of us have the same job. Some of us are consultants and designers. Some of us are regulators. Some of us are suppliers. Some of us are technical engineers who install or commission. And some of us are maintenance engineers. So the job function within AGL is varied, exceedingly varied. So what I've done here is just took really a design function, and I looked at a substation, and in today's day and age, we can use the technologies that are available to us. We can look at space allocations, etc. Never mind just the electrical side. You know, if you've got a piece of equipment and you've got to put it in a building, does it go through the door? And can it be lifted out if you need to change it? How many CCRs can you put in a space, etc. So what I've done there is just shown and maybe I'll go back to it. And I think it would be a good idea to go back and actually show this, because there's a little video here. Look, let me just show it. And there we can rotate it around in 3D. In 3D. And I think that's a good demonstration that in design technology today, then we use lots and lots of different design technologies to help us to not just design a substation, but for the equipment itself. So just a little example. And I've taken this from company Perfect Airport Solutions in Singapore, and this was for Myanmar, you know, in Southeast Asia during 2014. So I ask you, for power engineering, for power electrical engineering, do you have the knowledge and do you have the skill to look after the power side? I can't answer that question for you. You have to answer that question yourself. So let's move on to the AGL circuit itself. What's in the AGL circuit? Well, the AGL, it's all about lighting, meeting the photometric output in accordance with the isocandela diagram in Annex 14, Volume 1. And in ICAO Annex 14, Volume 1, every single light type whether it's an approach light or a runway center line or a taxiway edge light, etc. Each of those have their own isocandela diagram, and it's based upon the light output is based upon the candela or candela output. So let's go at the basic definition. The series circuit, it's a series circuit. That means electrical series circuit. It's not a parallel circuit or a series parallel. It's a series, solely a series circuit. A traditional AGL is a series circuit, electrical series circuit. And if you want some electrical theory training associated with the various things, then we can offer that. You know? However, the definition, a series circuit starts at the power supply, called the constant current regulator, CCR. And then it has a single loop cable all the way around the respective system. Whether it's a runway edge, it goes from the substation, a single wire, single core wire, from the substation out to the threshold, for example, up one side of the runway, across the end, down the other side of the runway, across the threshold, and back to the substation. Kilometers and kilometers and kilometers of single core cable. Now that in itself electrically is like a big capacitor. And then the lights are attached to this cable, but not directly through a transformer. And that isolating transformer is a current transformer, a one-to-one series current transformer. So that we have a primary circuit, which is the single core cable, and then we have a secondary circuit, which goes out to the light fixture in that format. So here we are, look, here's our substation where the CCR is, single core cable going all the way around and then back to the substation. And then we have these transformers and we have to connect the cable to the transformers. Now these connectors are designed in accordance with an FAA standard, a US Federal Aviation Administration standard. Now these connectors, they have to be watertight because this equipment, both the cable, the connectors and the transformers live under the ground in transformer pits, joined together by directly buried cable or through cable ducts. Cable ducts, part of the drainage system of the airfield. So they're all underwater. And I principally say, all waiting to fail. Because that's what happens. Over time, the equipment, it deteriorates in those conditions and it fails. So remember, safety. If you are going to have leakage from a connector, then you're going to have an electrical earth. And if you get multiple electrical earths in a field, that is 2 or more, then you are going to have an operational effect on your lighting system. Some of the lights will go dim or go out or flicker on and off. So, and at the same time, we are still have got a live electrical circuit. Of course, this design of the system, the standard system, means that a CCR will stay operating wherever possible. So earths in the field do not switch off the CCR, which makes it dangerous. So let's have a look at that basic circuit. We have the CCR, the power supply and distribution. We have that single core cable going all the way around. And then we have the transformer with the connectors. And then the secondary circuit, it's called, going out to the light fixture. How do we switch it on and off? Well, we have a control system. So the control system talks to the CCR, talks to the CCR in modern technology, and we're going to have a look at that through a fiber optic link and a PLC system. It will switch the CCR on and off, but it will also switch the intensity levels. And we will consider that at a different time. But we do have these intensity levels. Now, the intensity levels are defined by ICAO as 5 steps for runway. That is 100% of light output in accordance with the ISO Candela diagrams. 100%, 30%, 10%, 3%, and 1% as a percentage of light output. But the Aerodrome Design Manual from ICAO, part 4, there's some graphs in there, and there's a tolerance range. So ICAO's percentages are at the top of the tolerance range, but if you look at the current values that are in the IEC technical specification or in the FAA advisory circulars, they are at the bottom of the range. So there is a tolerance, and you must be aware of that. So what have we got? The 3 blocks of AGL, the distribution system, the lighting, the control system, controlling the CCRs, which puts the constant current supply out to the light fixtures. So there's just a list of what we have. Primary circuit, the CCR, lightning arresters. Not all manufacturers and CCRs offer you lightning arresters. So be aware. A lightning arrestor is that in the event of an indirect lightning strike and a voltage gets induced into the primary cable, then it could go back into the CCR and burn out the electronics in the CCR. So the lightning arresters is a safeguard to minimize that effect if that happens. There's also this thing called an output disconnecting device. It's offered from on many suppliers, and that enables you, and it's between the CCR and the field cable. So you can pull it out and push it back in, and it can be a multifunctional where you can put an earth on the circuit if you want to do some fault diagnosis. So an output disconnecting device is something as well. The cable. Now the cable is screened or unscreened. What do I mean by screened? It means that there is a protective screen, which is a conductive piece of material. It gives mechanical protection, but it also helps with electrical protection. Because if you put 2 cables together, and we look at the motor generator principle, if you put a current through one cable and you put another that is adjacent and it's alternative current where the magnetic flux is going up and down, it will induce a current into that adjacent cable. A screen cable helps to stop that. Okay, helps to stop that. So there is screen cable and unscreened. In our ICAO world, we use screen cable mostly. When you go to the US, then they use unscreened cable. Then we have these connectors, which I've already spoken about. Some nations actually don't use connectors. They use an inline splice, which is, they think is a better joint. But the thing is, an inline splice, a through joint, is more difficult if you've got a problem, if you want to break into the circuit. And then the isolating transformer, already mentioned the isolating transformer. The primary winding is on the primary circuit, yet the secondary winding is on the secondary circuit. And they are separated. They only connect electrically. They are not connected. Then we have secondary cable going out to the light fixture. For example, a transformer pit could be on the side of the runway or taxiway, which is its normal location, and it could be 30 or 40 meters to the light fixture. So we have a length of secondary cable, and then normally 2 core or 2 single cores, and that's connected to the transformer and to the light fixture with a 2-pin connector, where on the primary side, it's a single pin connector and the light fixture itself. Now, the light fixture itself has changed in more recent times. We've migrated from tungsten halogen to LED technologies. And the manufacturers are nowadays not really offering tungsten halogen. We're really only offering LEDs, although they still have to support tungsten halogen light fixtures. Other components in the system, though, is an earthing network. So we do actually put a common reference around the system in the form of an earthing network. But we also have something called a counterpoise system. Now, a counterpoise system is an earthing network, but it's an earthing network that is dedicated for lightning protection. That it is separated into installation from the primary cable, so that if there is an indirect lightning strike, this bare copper counterpoise cable will attract the lightning, the electrical charge, and safeguard the cable. That's the idea of it. The other aspect is interleaving. Interleaving then is mandatory. Every system must have a minimum of 2 circuits. That means if one circuit fails for whatever reason, then 50% of the lights in that system will still work. And therefore, from a pilot's viewpoint, then they will still see lights. Interleaving. So this is I've just did it as colors here, look. Red circuit, blue circuit. Ideally, you put the CCRs into separate substations. Of course, there has been times when a substation or a vault has burnt down. Well, if you've got both CCRs for an interleaved circuit in the same substation, then you're pretty knackered, aren't you? You're going to lose both circuits anyway. But if they're in a separate substation, then you've got safety. So design element and how you do that is really important. So coming back to the products themselves, we've only got 2 types of products. Those that we put into the pavement and those that stick above the ground. Elevated lights, inset lights, different models, different types. And in today's day and age, these lights are smart lights. That means that what we do with them, we actually, and we'll see on in surface movement guidance under the control side, we'll see that we put individual light control and monitoring equipment inside the light fixture. However, when we're looking at the technologies associated with lights, elevated lights, they could be many meters up in the air, like in an approach masts. But if they're inset lights, they're in the pavement. So we've got to have an understanding that how do we put them in a pavement? Well, the civil engineering knowledge to have associated that, because these lights, these inset lights, have to be put into a base unit that has been glued into the pavement. And then we have to bolt or screw the light fixture into that base unit. So not only have we got civil engineering understanding in AGL, we've got mechanical engineering understanding, because we've got to torque those screws, those bolts. And have an understanding, of course, about the electrical side and the electrical safety. So elevated lights, inset lights. So my question to you is, are you just a bulb changer? Or do you have the technology associated with being able to understand civil engineering, mechanical engineering, electrical engineering? And from a maintenance viewpoint, which will be discussed at a later date, then what happens if you go out there to change a runway centerline light and you're given 30 minutes to do it between flights, and you go out there and you've got a runway centerline light which has 2 screws, 2 bolts, and you shear a bolt? What are you going to do? You have to know what to do in that situation. Well, that's the skill. You might have the knowledge about civil, you might have the knowledge about mechanical and electrical, but do you have the skill and the nous, as some people call it, to know what to do in that situation? Let's move on. Control and monitoring. Control and monitoring. We need to be able to control and know what has happened. So what we have is, in terms of control and monitoring, we have various elements associated with a control and monitoring system. And I'm just going to flick on quite quickly onto this diagram here. And I have to say, I've taken this from ADB SafeGate's legacy control system. Why? Because it's a really nice little diagram to explain control system technology. What we have in there, we have the air traffic controller who has a screen, and he has a mimic panel, and he can see what's happening. He or she can see what's happening about the layout of his or her airfield, runway and taxiway network. But they need to be able to switch on and off the lights. So there's a lot of automated elements built into the control system to minimize that workload. But technically, they have to communicate down to the substation. And in today's day and age, then we tend to utilize industrial PLC technology. And that's been around for a long, long time. I know from my aircraft engineering days, we used exactly the same, but it was, instead of being digital, it was analog equipment. So as a helicopter, for example, a helicopter gas turbine control system was just the same as this. And the only thing is, it wasn't a PLC, you know, it was lots of analog circuits. But the principle is exactly the same. To be able to communicate from the air traffic controller down to the substation, then we don't have lots and lots of kilometers and kilometers of hard wire anymore. We maybe have a fiber optic network. And so we have to have fiber optic converters. So we have the human machine interface, the HMI, up in the tower, talking via a fiber optic converter through a dedicated fiber optic network or a shared one, because this happens, down to the substation where the PLC is, and the PLC then can communicate to the CCRs and communicate either by a digital, a database, a data communication system, or hardwire. Then there's those two options. Hardwire is quite good for us in the maintenance because you can actually say, oh, well, it's either 24 volts or 48 volts. So you can actually go in there and say, oh, yeah, I've got a voltage. But when it's a data, you can't. It's a little bit, it can't be seen. Eh? So there is, do you understand this technology? That's my question here. Because it's a different part. It's electronic and IT technologies here involved, not just changing the bulbs in the airfield. If you go to more complicated, a complex aerodrome, then there could be multiple substations and even a control tower, maintenance control center. So what we do is to have multiple systems like the first one, but more of it. And then at the same time, we do our belt and braces. Then we'd have a dual PLC system, a master and a slave. And we'd have a dual fiber optic network in case we lost one, or even a server system, or even a dual server system. So this is building up the complexity of a control system. But I'm not going to go into the detail of how it's done. It's just an example. So moving onwards, and I would say, do you have the skill? Do you have the knowledge? And do you have the skill for this electronic engineering? So we're changing the bulbs in the field, we're changing the light fixtures in the field. we have to have an understanding about distribution networks and electrical distribution. We need to have mechanical engineering understanding. We need to have civil engineering understanding. We need to have power engineering understanding. This is all part of AGL. We are multifunctional, definitely multifunctional. And now we've got modern remote control system technology. How are you going to manage that? How are you going to be able to do that? Only you can answer that question. Are you multifunctional, or do you need to split the jobs? It's a question I can't answer. You've got to look at your own airfield from that respect. So let's move on to some of the operational needs.
Keith.
Oh, hello,
Keith.
Robert. I see you now jumped into us, eh?
I just very much enjoying your presentation, but unfortunately, time is flying, and I think at this point it would be a good moment
maybe that's a good idea, because you know what I was going to do on here is just to introduce, to say that, you know, our world has changed, as we know, both operationally and technically. And as we go on to the next phase, there's a little video which introduces it. So if we show the video this week, and then next week we can move on to that by moving into these technology changes. Shall we do that?
Okay then, Keith.
That's a pretty good idea. So look, here's a little video which shows how AGL is now utilized today in airports.
Yeah, 6250, ready for taxi. Iberia 6250, heavy, Kennedy ground. Section taxi on Alpha, and that Victor turn right Bravo. Okay, Victor right on Bravo, for the shut off whiskey. Vehicle 9870, Kennedy ground, first going to right at Foxtrot. Target 9870, right at Foxtrot. Ground Shepard 143. Vehicle 97, roger. Ground Shepard 143. American 181, can you get by? Flagship American 181, just stand by there. Flagship on 318, turn right on the field, left on wrong with 4 left, go to Hondo. Railroad 413, follow Eagle and Brea from your right, cross only to right, here to Quebec, monitor the tower 123.9. We're going to follow Eagle across 20.9 or Redwood 413 tonight.
Thank you.
And that was interesting there, you know, because you mentioned the webinar earlier today, you know, by Honeywell, TKH and Midstream, yeah? And it was interesting that the Honeywell presentation was about their Navitas system, which is very similar to that, does the same function really as, with maybe a few added features as the system I've just shown on that little video. Yeah. It's an ideal time because then we can move on to the technologies of individual light control and monitoring, surface movement guidance, etc., and some of the new technologies like SED. You know, the contactless switch also was in that webinar this morning.
Keith, okay. we have one specific question about that. Osvaldo in Mexico would like your opinion about the pros and cons of new inductive technologies such as SED.
Yeah, well, if he contacts us directly, via this link, I'd be very happy to, because it is quite a you know, it's new technology, and as it was explained this morning in their webinar, the IEC, the International Electrotechnical Commission, they are changing their documentations to enable it to be a technical solution for AGL.
Right. So we had some questions from Engineer Mohammed Azjad in Islamabad International Airport. He wanted to know. He had 3 questions. Can we use a proportion? Can you mix halogen and LED lights on a runway?
The guidance is you do not. You do not. And now when LEDs were first introduced, they were first introduced at taxiway edge and then into taxiways, and then eventually we're enabled to use them as stop bars for runway incursion. And it's only not too many years ago that approval was given for runway related lights. But the guidance from the authorities is you do not mix runway related lights between tungsten halogen and LEDs. No.
Thank you, Keith. His second question was relating to the Amendment 44 to the Annex 6 Part 1. So this is the Cat 3 question. Are there going to be changes to the Cat A, B, C designations?
Well, that's very interesting because Annex 6 is due for re-release at the end of this year, sometime. We're currently at edition 11, and Amendment 43 is in edition 11. Now, Amendment 44 has been discussed, and one of the aspects that we're looking at is about decision heights, I believe. And so we have asked for some clarification from ICAO on exactly what the Amendment 44 encompasses. But if you look at the current standard in Annex 6, plus in Annex 14, of course, which is our guideline, then Category 3 is 3A, is when the visibility, RVR visibility, drops below 300 to 175 meters. And Category 3B is 175 meters down to 50 meters. And Category 3C is RVR below 50 meters. But in each case, for Category 3A, there's a decision height that the pilot has to decide that at a particular height from the ground, then can he or she think it's safe to land? Otherwise, they have to go round. Now, that decision height for Cat 3A is currently between 60 meters and 30 meters from the ground. And Category 3B is currently below 30 meters, and there's no requirement below for Category 3C because it's basically an instrument landing, you know, and they can't see, you know. So that's the criteria that is being discussed, whether or not the RVR and particularly decision height element needs to be changed based upon, of course, most aircraft will land on the instrument landing system, you know, so it's an instrument landing under the ILS rather than visual.
Good. So there's more on that coming later this year.
Yeah, more to come. You know?
Yeah.
Yes.
Mohammed has also, his final question was relating to the value of insulation resistance. What insulation resistance is considered good for an average length underground AGL circuit, and how should we calculate that? Good
question, eh? Now, there is some guidance on this from ICAO and from the IEC in the technical specification 61820 and ICAO in the Aerodrome Design Manual Part 5 for electrical systems. The acceptable insulation resistance value for a primary circuit is based upon a calculated value. And the calculated value is based upon the number of transformers that you have in the primary circuit and the length of the primary circuit. So those two factors are in the equation. So every single circuit, AGL circuit, on every airport all over the world is different. It has a different length and different number of transformers, isolating transformers in. So we calculate, and it's the earth leakage calculation that we calculate first. Earth leakage, what I mean by that is that for every transformer, we are allowed to have 2 microamps leakage to earth in our field circuit because of where it lives. And every 100 meters of primary cable in a circuit, then we're allowed to have 1 microamp leakage to earth. Now, bear in mind, then there are multiple lengths of primary circuit and multiple numbers of light fixtures, hence multiple numbers of transformers, because it's 1 light, 1 transformer normally, okay? So we calculate it. Now that gives us the minimum acceptable value. Now there's some criteria then, that is compliance. If it is above that minimum value, it is compliant. That's as simple as that. But we don't want our systems to work at that minimum value or just above. So there are factors that we bring into the equation, and the factors that we bring into the equation is what's the acceptance criteria on a new installation. And therefore that should be in the documentation associated with the acceptance criteria. It could be 1 gigohm, 2 gigohms. It could be very, very high. But when it comes to maintenance, and maintenance, we do maintenance. Remember, we do breakdown maintenance, and in this case, below the minimum level, or we do preventive maintenance. So you're going to start to do maintenance before it becomes to the minimum level. So there is some very generic, unwritten guidelines that we use in the industry, and that depending on whether you live in a wet environment or a dry environment, then the guidelines, you put an alarm level. So when you start maintenance at either 2 times the minimum value or 5 times. However, from a management viewpoint, maintenance management, you might decide to have it at 10 times. You know, you have to decide how critical and what risk is associated with the deterioration rate is of your equipment on your airfoil in your location in the world. So it's a big subject. So if you would want to discuss it, you know, it's when I do our training courses, we spend, you know, a day or 2 talking about this very subject and doing all the calculations. It's very important for us to understand, because if we fail to get that correct, our system could kill us because we've got earths in the field.
Right, thank you, Keith. We've got a lot more questions coming in, but I'll just take 2 more questions if we may, and then we will put all of the answers for all of the questions into our Q&A session for the.
And we'll convene again next week at the same time. Yes,
we will. The last 2 questions. Ilya has asked you to explain field lighting arresters, their application and earth values with and without them.
That's again, it's in the same subject of longevity of the insulation resistance values. When you're talking about lightning arresters, you're talking about lightning arresters, and what is the function of a lightning arrestor? It is to protect the system against an indirect lightning strike. If you get a direct lightning strike, then I'm afraid, you know, there's nothing going to be left, right? Not at all. But there has been a lot of investigations, particularly in the US, and because they use unscreened cable, it's really relevant to them. Where in the ICO world, we use screen cable. So in an on-screen cable world, they need to protect that cabling. And therefore, a lot of discussions have gone, a lot of investigations. And in principle, they said that when a lightning strike hits an airfield, which is a big wide open expanse, and which we should not be out there if there's lightning, then it hits the pavement first, and then dissipates across the surface of the pavement into the soft, into the grass, and then dissipates slowly. And so what we do is to have this counterpoise system, this cabling system, bare copper cable of quite a large size, and so it's actually expensive, and because it's copper based, and then we actually place it either above or pavement side, slightly above and pavement side of where the we're laying our primary cabling, or even a network. You know, so it really is a big subject. So if he wants to contact us, you know, separately, you know, we can give some advice on the lightning arresters. But what I would say to him is really check whether your CCRs have got lightning arresters built in, because that's the first step to protect your CCR. And then the second, if you're in an area that are prone to lightning, or shall we say, electrical storms, then do you need to have additional lightning arresters, or surge arresters, as some people call them, which are external to the substation in the field. Okay?
Right. One last question there. Concerning, you were talking about interleaved circuits earlier, and Mohammed would like to know, could you have 3 or 4 interleaving circuits?
The answer is yes. If you go to South Africa, for example, they have 3 interleaving circuits on their runway centre lines. And the idea of interleaving is that should one circuit fails, that the pattern remains similar. And I think the actual word is uniform, you know, so that, you know, you have to have a bit of a consideration that when you've got lights, for example, you've got a taxiway centerline light, or you've got a taxiway edge light, or then all of them are the same color. But when you've got a runway edge and when you've got a runway centerline, then the color changes when you're nearing the end of the runway. So in that, let's take a runway centerline. They're all white in color until they get to towards the end of the runway at the predetermined distance, and they go red, white, red, white, red, white. And then at 300 meters from the end of the runway, they're all red. So that red, white, red, white, red, white area, then do you have 2 circuits, which is the minimum, or do you have 3 circuits, or do you have 4 circuits? It doesn't matter, you can. The only trouble is if you've got more circuits, you've got more cable. You've got more cable, you've got more connectors. You know, there's a cost and a maintenance issue associated with it.
Thank you, Keith. And thank you very much for a very, very informative and helpful presentation. I hope everybody out there also found it similarly interesting. As I said at the beginning, we're going to go into a 4th week to continue this topic, and then moving into new technologies. We will also be doing Q&A session, more of your questions. There are a lot more coming in, I can see. We will answer those directly, but also possibly expand on them in the actual webinar next week. For everybody out there, the key to aviation recovery is a coordinated approach from our regulators and national organisations. But for us on the ground, the key thing is to be ready to manage the risks from the closures, and to make sure our preventative maintenance is up to date. If we at TMS, Keith, myself, any of my colleagues, can be of any help, please don't hesitate to contact us. And if we can't answer the questions, we'll find someone, which is very unlikely, knowing Keith. If we can't answer the questions, we'll find someone that will. We will also be sending out details about our plans for a PAPI webinar, a maintenance of visual aids and safety in particular webinar, and also an asset management webinar. So thank you so much for your participation today. It's absolutely fantastic. I can see there are 100 of you out there. Very much appreciated, and look forward to seeing you same time, same place next week. Stay safe.
Stay safe.
Thank you very much. Goodbye.